In this video, we're going to take a look at integrating trigonometric functions. So right now, there are really just only a few trig functions that we're able to anti-differentiate. We can do sine and cosine, and then we have, for instance, secant tangent. We know that by simply using the reverse of a rule from uh, differentiation. But the question is, what about if we just consider our 6 standard trig functions? What is the antiderivative of tangent, for instance? Or what is the antiderivative of secant, or cosecant, or cotangent? So let's take a look at those. And what I will do is I will show you the procedure for deriving the result for the antiderivative of tangent, as well as the antiderivative of secant, and then I'll state the result for the other two, for cosecant and cotangent, because the process is very, very similar. All right? Okay, so again, let me just kind of state what we know. We know that the antiderivative of our sine function is negative cosine of x plus c, and we know that the antiderivative of cosine is the sine of x plus c, right? So basically, of the 6 basic trigonometric functions, we have antiderivatives for 2 of them, right? Now we're going to say, well, what does it look like when we integrate tangent, right? So let's see if we can figure this out. Well, what do we know about tangent? Tangent can be written as the sine of x divided by cosine of x. So I could do that. Right, dx. And if you think about like whenever we have a certain type of fraction, again, if it's not something that we can reverse like quite easily, what we tend to do is we ask ourselves, well, can I use some kind of substitution? So you tend to look at the denominator and say, well, is the derivative of the denominator like a constant multiple of the numerator? And it is, because the derivative of cosine is negative sine. So if I let my u be equal to cosine of x, then du is negative sine x dx. So all I'm missing is a negative in my problem, but we know how to fix that. Multiply both sides by -1. So we have negative du is the sine of x dx. So that means I can replace sine x dx with negative du, and then I can replace the cosine of x with my u. So the integral becomes, I'll write it as -1 over u du. Now this negative sign we can take out of the integral. So it's negative of the integral of 1 over u du, but that's our natural log. So this is negative the natural log of the absolute value of u plus c. Now I'm putting the absolute value because, again, we have no idea if u is positive or negative, and this is a valid antiderivative of 1 over u. And then let's go ahead and reverse the substitution. So here is one form that we can write the antiderivative of tangent in. It's negative the natural log of the absolute value of cosine of x plus c. But it can also be written, let's say you don't want that negative coefficient. You can use the property of the natural log, bring up that negative sign, and make it a power of the absolute value of the cosine of x, right? You can that's a property of natural logs, or not just natural logs, any logarithm. And then there's a property of absolute absolute values that allows me to bring this negative inside, right? So this is the natural log of the absolute value of the cosine of x raised to the -1 power. So that's the reciprocal of cosine. The reciprocal of cosine is secant, and this is the other form that is useful when integrating the tangent function, right? So you might see either this being used or this being used, all right? So now we can integrate our tangent function. Now it turns out that it's very similar for cotangent. The antiderivative of cotangent is the natural log of the sine function, right? So let's write that down. Right, so I'll write this over here. So the antiderivative of the cotangent of x is the natural log of the absolute value of sine of x plus c. And this is a nice result. It works very similarly to how we would derive the antiderivative of tangent. The difference is cotangent is cosine divided by sine, so your fraction here gets flipped, which means you end up using u equals sine of x, and you don't even have the negative sign to worry about anymore, right? So this is something you should try and derive in your own time, just so that you can see the process and see how it works, all right? So good, we're up to 4, right? So now we can anti-differentiate sine, cosine, tangent, and cotangent. So that leaves secant and cosecant. I'll show you the result for secant and then write down the corresponding result for cosecant. Now, the one for secant is a little strange. It's like, why would I even do that? Well, because it leads to a solution. That's why. So what we do with secant, if we think about from Calc 1, what do we know as far as derivatives that involve a secant function? Well, we know that the derivative of secant itself is secant x times tangent x. We also know that the derivative of tangent is secant squared, right? So knowing those two things, this is how we're going to modify this function to get this process to work. I'm going to think of this as secant x, right? So secant of x over 1, and then I'm going to multiply the top and the bottom by something. We're going to multiply it by tangent x plus secant x. So multiply the top by that quantity and the bottom by that quantity. You're thinking, why would I do that? Well, it turns out when you do that, in fact, let me write the, since this is a sum, let me write the denominator just in a different way. I'm going to write it as secant x plus tangent x dx, all right? So basically, what I'm multiplying here by is 1, right? But what I'm going to get in the numerator is actually going to allow me to use a pretty clever u sub. So we have the antiderivative. Now if I go ahead and distribute the secant in the numerator, I will have, look at that, secant tangent, and then plus secant squared. And then in the denominator, what do I have? I have my secant x plus tangent x. And these were the derivatives that we just said. We stated that the derivative of secant is secant x tangent x, and the derivative of tangent x is secant squared. Why does that help? Well, if I use the denominator, that same old trick, using the denominator as my u, this is what I will get. So if we let u equals secant x plus tangent x, my du is going to be, well, the derivative of secant is secant x times tangent x plus the derivative of tangent is secant squared, and all of that times dx. And that's exactly what we have in the numerator here. So all of this big expression here, this product, that is du, and then I have my u in the denominator, right? So we end up having this result. So now when I write the integral in terms of u, I have the integral of 1 over u times du. And all these other four trigonometric integrals, tangent, cotangent, secant, cosecant, they all involve ln. And you might be wondering, where does the ln come in? Well, it's because they all end up having some kind of clever little u sub where you end up letting your denominator be equal to u, so you always end up with this 1 over u form, right? So here's our final answer. So the natural log of the absolute value of u plus c, and then we reverse the substitution. We don't have any limits, and now we have a result that we can use anytime we have to integrate the secant function. So it's the natural log of the absolute value of secant x plus tangent x plus c, right? And that is the antiderivative of the secant function. Now we can do a similar result for the antiderivative of cosecant by, again, expressing it as cosecant over 1 and multiplying by a certain fraction, and that results in this antiderivative. So let me write this one down. Right, so cosecant of x, again I'll just write this result down, and this one ends up being the negative of the natural log of the absolute value of cosecant x plus cotangent x plus c, right? So now we have the antiderivative of all 6 trig functions. So it feels like we should just go ahead and summarize them. And there are patterns in these. So we have the antiderivative of sine x is negative cosine x plus c. Antiderivative of cosine x is negative sine x plus c. The antiderivative of tangent x dx, that's the ln of the secant of x plus c. The antiderivative of cotangent x dx is the natural log of the sine of x plus c. And then maybe I could squeeze these in over here. The antiderivative of secant x dx is the natural log of the absolute value of secant x plus tangent x plus c. And then finally, the antiderivative of cosecant x dx is negative the natural log of the absolute value of cosecant. There we go. So cosecant x plus cotangent x plus c, right? So all 6. So part of the reason why we need these, right? And it's not that these integrals by themselves are earth-shatteringly important. I mean, they are. But it's just that in future integration techniques, many times we're going to take a problem and reduce it to, an integral that might end up having tangent or secant or cosecant. And then we have to be able to, in order to complete those problems, we have to know what the antiderivative of these 6 trig functions are. We knew these 2, but we didn't know these 4. But now we know, and knowing is half the battle. Okay? All right, I'll see you in the next video when we're going to work on some more trig antiderivatives, and these will involve powers of sine and cosine and powers of tangent and secant. See you then.